truthful mechanisms or combinatorial options with submodular bidders, and it's by Sepehr, Assadi, and Singla, and it's Sahil that will give the talk. So
thank you.
Please.
Hello, everyone. Okay, so I'll be talking about some combinatorial auctions with submodular bidders. And this is joint work with Sepehr Assadi, who's currently an assistant professor at Rutgers. He's sitting in the audience. And yeah, this work was mostly done like when he was still up at Princeton as a postdoc. And okay, let me give you start with an informal introduction, like what's the main setup. You have a bunch of items and a bunch of bidders. So in particular, N is the number of bidders and M is the number of items. And the high-level goal is you want to just distribute these items between these bidders so as to maximize their happiness. So, and more formally, you have these M indivisible items, so you cannot divide them. But they are not identical as well. So, I mean, although in the figure they look identical, they're not identical. Every bidder, like these, whatever, cows, turtle, they have their some valuation functions. Know their valuations are private, but for a moment, let's ignore what private means. So, but each of them has some function which defines their happiness. This is called as their valuation function for any subset of items. And your goal is to maximize the total happiness, which is the sum of the happiness of everybody. So player, bidder 1 gets set S1, bidder 2 gets S2, and this is a partition of all your items. So you want to maximize the total welfare. And now the valuation functions could depend, belong to many classes. The simplest class is the additive, where your valuation for two items A and B is just the sum. More complicated would be submodular, beyond that XOS, subadditive. Basically, the more general you make the class, the problem becomes harder. And okay, we want to kind of study all of them ideally. So that's the high-level goal. And okay, let's see what we can do. Let's for a moment talk about just the purely algorithmic question, where I remove all the game theory out of it. In particular, assume you know all the valuations up front. So can we then efficiently maximize welfare? So by efficient, I mean polynomial time, either the running time or the number of oracle calls. So as a warm-up, if the valuations were additive, I claim this is very simple, because basically you can do is each item, just assign it to the person who values it the most. Simply because two different items, they don't really interfere with each other. Just give the item to the person who likes it the most, and that will already be optimal if you know the valuation functions. As soon as you move beyond additive, like submodular valuations, it's first of all unclear how are you even given access to these valuation functions, because you need an oracle. It's unclear. I cannot give you for every subset what's my valuation function. That's exponential size description, 2 to the m. M is the number of items. But the usual way around this in TCS, we've been taking, is the oracle model. So one popular oracle is the value oracle. It's basically some black box whom you can give an input. Okay, for this particular set, what's your valuation? What's the happiness you get? So you can imagine you have n such oracles, one for each bidder. And in this case, it was already shown by LEMMA and Nissan in 15 years ago around, that basically this additive algorithm that you were saying, pretty much a slight variant of this, already gives you a half approximation, a constant approximation to the optimal welfare. Basically give the item to the person who has the highest marginal value for it, rather than just the plain value, the highest marginal value. That gives you a constant approximation. And we know actually better, over the years, we now, you can even get a 1 minus 1 over E approximation, but okay, you cannot hope to get 1, basically. They're information theoretic bounds, in polynomial number of oracle calls. There's another oracle, the so-called demand oracle, which is stronger. It's more powerful than the value oracle. The reason you kind of need it is already, if you go beyond submodular valuations, something like XOS or a subadditive valuations, it's known that using value oracle, you can only get some polynomial approximation. You cannot hope to get a very good approximation. On the other hand, if you give me this more powerful demand oracle, I'll define this oracle a bit later. It will appear later. But the takeaway is that if given this powerful oracle, then basically you can get constant approximations for this entire class, even subadditive valuations. And this was a result of Uri, who might be in the audience. Okay, so the main question is that, we know how to get constant approximations if I remove the game theory out of it. And now if I put these strategic bidders, where you don't know their valuation functions, can you still get constant approximations? That's the high-level motivating question. And so, okay, what's formally it's called? You have these M items. You have a bunch of these bidders. Now, all of them are strategic, or you can call them selfish. Basically, each of them wants to work in their own interest. And they have their private valuations. So you don't know their valuation functions up front. What your goal is to come up with a mechanism. You saw this, I think, even in the last talk as well. So truthful mechanism, which is you can say just an algorithm, which takes as input the valuations of different people, and it outputs two things. One is which person gets which set of items, and how much they're going to pay for it. So you get an allocation, like set S1 to Sn, and some payments P1 to Pn. And what's your goal? Your goal is to maximize the welfare. As before, you want to maximize, you are, say, the government, you want to maximize the happiness of the society. Whereas each of the individual bidders is trying to maximize their happiness, which is their valuation minus the price that they pay. So these individual bidders care about money, but you don't really care about money. You're the government, and sometimes you're just trying to maximize the welfare. And the property you want from this mechanism is it should be truthful, that the valuations that these people are reporting, they should have no incentive to lie. I mean, the reason you kind of make such an assumption is because if you give them incentive to lie, then the system is not at all stable. Everybody behaves in a different way, and there's not very hard to predict what's happening. And the question is, can you come up with such a mechanism? In particular, we also care about polynomial time. So classical result of Vickrey, Clarks, and Groves, they show that actually this is always possible. It's like a generalization of second price auction, which shows that there exists a truthful mechanism which gets you the optimal welfare. The problem is it's not efficient. Not efficient as in it does not run in polynomial time. Primarily because even the submodular problem that I was telling you, the offline version, offline as in the purely algorithmic, you cannot already get a one approximation. You have to lose some constant approximations. And if you try to combine that with VCG, you're in trouble. So it doesn't go through. And the main question is, can you get a truthful mechanism, which is both polynomial time, and now I'm willing to lose a little bit in my welfare guarantees, because even in a purely algorithmic, I was already losing a constant factor. And what can I achieve here? So what's known? So the first result is actually in the value oracle model, it's pretty much hopeless. You cannot hope to get better than a polynomial approximation. So this was a result of Shahar Dobzhinsky and Jan van Rack. But if I give you the more powerful demand oracle, it actually gives you a lot of power. In particular, you can start getting some polylogarithmic in M approximations. So over the last 15 years, these approximation factors have been improved, from log square M to square root log M. And the main driving question is, can you actually get something close to the purely algorithmic question, basically a constant approximation for this problem? So in this paper, our main result, we still don't answer this fully, but we make progress. We get from polylogarithmic in M to polylog log M. So we're getting some kind of an exponential improvement. It's log M cube in particular. And the results also extend to XOS valuations, this larger class that I was telling. We still don't know how to make it work for subadditive valuations, but up till XOS, we can get some log M approximations. That's the main result. Good. So here's the outline. So I just give you what the result is. I'll give you some preliminaries on what are fixed price auctions, and then how our mechanism, the price learning mechanism works, and a brief idea about its analysis, the main lemma. So fixed price auctions are kind of you can say the simplest auction you might think about. It's saying okay, you set up a price for every item, and each person who walks in, they can take any arbitrary subset of the remaining items. So suppose you walk into a grocery store, the first item is at $1.10, second at $1.20, third at $5 or something. I allow you to take any subset of the remaining items. Of course, you cannot take an item which has been already sold out. Amongst them, you just take so what would you do if you're the ith person? You'll basically maximize your valuation minus the price. Crucially, your valuations could be submodular or any combinatorial function, but the prices are additive. Good. And this is one of the simplest auctions. And why is it interesting? Because of two primary reasons. First of all, it's very trivially truthful, because each person only gets to pick items once, and the prices are never going to go down. So it's in their best interest to actually take whichever set they like the most. They don't want to misreport or anything. Also, it's efficient. That's kind of, you can say it's slightly cheating, but it's just by definition of demand oracle. So this more powerful oracle, demand oracle that I didn't define before, it's precisely defined in this way, that if you set up the prices for the items, then this oracle returns you what's the set that this person is going to buy. So just by definition of demand oracle, and which seems reasonable in some assumptions. You should at least be able to go to a grocery store and decide what to buy. And good. Now, so it's both truthful and efficient. The question is, okay, what can I guarantee about welfare? Remember, we wanted to optimize in all these three parameters, like truthfulness, efficiency, and welfare. And one folklore lemma, so we're not sure exactly who first showed it. There are like many variants of this lemma that have appeared. But the takeaway is that for submodular and XOS valuations, there always exists some prices. I'm not telling you what are these prices, but there always exists some prices, such that even if you just run these fixed price auctions using these prices, you already get a good approximation, in particular like a constant approximation, a 2 approximation to your welfare. So there exists some prices. And like some people, roughly the idea is that comes from like the definition of XOS functions. So you won't need it later, but if you've heard, so XOS functions are nothing but max over a bunch of linear or so-called additive functions. And from this definition, some naturally a price can be defined. Look at the optimal allocation, so whosoever get which set of items, whichever additive function achieves this optimal value, you can define a corresponding price for each item. But you don't need to worry about how exactly it's defined. The main point is that there exists some prices, that if you run fixed price auction based on that, you're already done. And so the rest of, the main question is, okay, how do I find these prices? And let me give you a very simple idea how you can already get a log M approximation. So this already matches in this long list of work I was showing, already a second or the third result. And the idea is very simple, getting this log M approximation. Basically, you do some kind of exponential bucketing. Okay, so first, one corner case, to handle corner cases, with constant probability, I'll just run a second price auction on, imagine I just bundle up all the items together, and imagine it's just a single item. So on this entire bundle, because now I'm left with a single item, I can run an approximate, a simple VCG, a second price auction. So this is easy. This is just to handle corner cases. But the main idea is otherwise what you do, just partition all your bidders into two groups, say N0 and N1. This is a random partitioning. For the bidders in N0, you just say them, okay, unfortunately you had a bad day today, so I'm not going to give you any item. But please cooperate with me, still tell me what are your valuations. So notice these people, they are not going to get any items. So their valuation is going to be 0, their payment is also going to be 0. So it's a 0 minus 0. So it's still, they can cooperate, they can tell you their valuations. They're not getting any items. And so that's mathematically allowed, and practically it's kind of saying okay, you're conducting some kind of a survey. The only goal of this process is to get some estimate of opt, a constant approximation. So you need to know okay, are you aiming for $100 in the game, or are you aiming for $1 billion? You need to get some estimate of what opt is. So using this simple trick from these bidders N0, the first group, I can already get using concentration, I can already get a decent estimate of opt. The only cases in which it does not work is when there's one bidder which has extremely high value. But remember the first step when I was running the second price auction, it will handle all those corner cases, so you don't need to worry about. So for the rest of the talk, assume you know opt. And now once you know opt, you're done, because you can easily show that all the prices, these prices that I was talking in the fixed price auctions, they only belong to some polynomial range. In particular, they have to be between opt over 2m, constant times m, to opt, because any item which is priced much lower than this, it doesn't really contribute. There are m of such items, they don't really contribute too much to your optimal welfare. And once you have this polynomial range, you can just guess the price for each item. By 1 over log m probability, you'll be fine. And that's it. So just run the fixed price auctions with respect to these guessed prices and on the remaining bidders, the N1. And notice I'm only arguing about my expected happiness. I'm not claiming that, okay, with high probability, I'm getting you a high, good welfare or something. But the point is with 1 over log m probability, I'm getting a good estimate. Good. So, and okay, if you want to go beyond log m, in particular, we are interested in log m, then you need to somehow estimate these prices better. I don't want a polynomial range, I want a smaller range. In particular, if I have a log m range, then I'll be done, because then I can do a log m. So what's the high level idea? So, it's kind of natural, rather than just partitioning these people into two groups, I partition them into many, many groups. So in particular, I partition them into beta groups, where beta is log m. So notice I'm looking for a beta cube approximation, so poly beta. So what I do is I partition all these bidders into beta plus 1 groups. imagine you already know opt. I mean, like using the simple trick that I mentioned like earlier by ignoring the first half of the bidders, you know opt. So you have these bunch of these bid groups. The idea is the following, that in the beginning you'll set very low prices. Say I set all the prices to 1, opt is M. Whenever a group arrives, you'll offer them these items at the current price P, which is initially set to like very low 1, with a small probability, and you ask them, okay, are you going to purchase these items or not? So you ask them like one by one, which set of the remaining items are you going to purchase? With a small probability, like 1 over beta. Like 1 over beta is not so small in the sense, like, okay, I'm looking for a poly beta approximation. But with 1 over beta probability, I just say, okay, what the items that you pick, these are yours, and the game ends. So that's the entire mechanism. But with most of the probability, like 1 minus 1 over beta probability, I say, okay, unfortunately, you also had a bad day. I'm not going to give you any item, but I'm going to use this information, like the fact that you were purchasing these items seems like these items are in demand, so I'm going to raise their prices for the remaining people. I'm not going to offer these items again to you because, I mean, if I offer them again, maybe you have incentive to lie. So I want my mechanism to be truthful. So I just raise up these prices. So all the items which get sold, I'll increase their prices and I'll continue. In particular, like, finally, by the end of the game, like to the last group, you will have, I mean, your hope is that you have like a very good estimate of what are the correct prices, like up to like say a log m factor, and then you can get like a log m approximation. So the main takeaway is like you're using these fixed price auctions as a proxy to learn the prices. And like it sounds intuitive in some sense that like, yeah, whenever an item is in demand, you'll just raise its price. And okay, you need to be careful about like how you exactly increase the prices, but it's not terrible. I mean, roughly what you're doing is you're doing some kind of a binary search. So what do? Like you have some tree. In the beginning, you have like these log m buckets in which price of each item may belong. In the next round, like for the next group, your hope is that, okay, I can shortlist from these log m buckets to log m over 2 buckets. In the third round, like log m over 4 and so on. And what you'll do is like, okay, I'll first, in each round, I'll set first like a low price and then a slightly higher price. If you are purchasing at the higher price as well, then I know in the future I'll even search higher. Basically like a binary search. But of course you need to do everything a bit carefully. But at a high level, what you're doing is just a binary search. So you'll run these, and in each round, you're just running these fixed price auctions with the current price. With a small probability, you actually stop, you give them these items. Otherwise, you just continue and raise up the prices, And so the crucial thing is like each item has a separate root leaf path because each item will have like a different price. So I'm doing this like for every item separately. And there comes like now what's the main lemma, the analysis, is we call it the so-called like learnable or the allocatable lemma. Roughly the intuition of this lemma is it's saying the following. In any round, so if I'm done with like round I minus 1, in the final round, what do I want? Like in this ith round, I want either most of my items are getting sold and I'm getting a better estimate of their prices. So if initially I knew like the prices belong to some log m buckets, in the next round I can tell you that they are belonging to some log m over 2 buckets. So either in each round, I'm getting a better estimate of the prices, or the second step is saying like the current prices are already pretty good. So even if you just run a fixed price auction with respect to the current prices, that already gets you like a poly beta approximation. And notice, I mean, you need like a either or kind of a condition because you cannot hope to always learn the prices very good. Suppose there's an item who like is being valued only by a single person. You cannot use other people to learn like the precise value of this price of this item. But the point is, okay, if even though you cannot learn its exact price, many prices are good for it. So it will still give you like a good allocation. So the main lemma you want to prove is the so-called like learnable or allocatable, where either you are learning that, okay, you can get a better estimate of the price in this round, or the current prices are already good enough. And this proof will very crucially use the fact that, okay, that you are like these bidders are arriving in a random order. So there are like also some connections to secretary problems and everything, like which I have worked on. But the point is, yeah, I mean, the main takeaway is it sounds intuitive as well. I mean, in some sense, what you're saying is for this item, for any item, either the price is already good, or there are many people competing for this item. And if there are many people competing for this item, then some of them is going to attempt to buy, and then you can bump up the price. So you'll learn a better estimate. And once the competition for this item goes down, then anyways, you're in a good shape. The right person will hopefully arrive and take it. So just to wrap up, If you're always learnable, you're getting a better and better estimate, then you're good, because by the last round, you'll have a very good estimate of the prices, correct prices, and then you can just randomly guess. Otherwise, if you were ever in a case that, okay, the current prices were already good, there was a 1 over beta chance, remember, that I would just stop here. So by losing like another 1 over beta factor, which I'm fine, I'm already done, inductively argue. So to conclude, we get like a log m approximation, like polylog m, using fixed price auctions as a proxy to the learning prices. And there is this binary search tree, which we are doing. There is this learnable allocatable lemma. The main question is, okay, can we get a constant approximation? I mean, we still don't know anything about this. And we already know, I mean, log m cube is not tight. I mean, we can make like some small improvements in it, but still our approach is stuck at like log m. I mean, we cannot hope to do like really much. And again, like extending to subadditive valuations, again, we don't have many ideas. Because usually, like for subadditive valuations, you do is like you reduce them to XOS valuations and then do for XOS. But this reduction uses like a log m factor. So it gives you like a polylog m, but if you want like a log m, you need some new ideas. And that's it. Thank you. Yeah. You're saying like, do we have a black box reduction? We'll have to check carefully. I'm not sure. So we are using a bit more than like just any fixed prices being working. We use like in like particularly one of our steps, we use the fact that bidders are arriving in a random order. So that also gives you like a good valuation, like if the current prices are like a bit low. So I'm not sure if there's like a black box reduction to I thought your question is like, yeah, for subadditive valuations, if there exists some posted prices, good posted prices, then are you already done? So I'm saying like, I don't think we have a black box reduction, but we should check it.
Is there like some conditional posted price mechanisms on which would work?
Probably, we haven't thought about it. Probably, I mean, we are not using too much from the posted pricing mechanism, so I think probably like we need very weak properties, but we might need something we should check. Yeah, we haven't checked. Yes?
Yeah, you mentioned the results extend to XOS. Is that sort of directly, or do you have to modify the argument a little bit?
It's direct. Actually, for submodular valuations, we don't prove anything. We actually just prove for XOS, and yeah. And the reason basically being like XOS, by definition, they are like max over these linear functions, which implies that there exist some prices, and submodular functions are known to be XOS. So, I mean, yeah, basically the entire proof is for XOS. I mean, we don't really do anything for submodular. Thank you.